Hi, welcome back to my channel. This is Harshita from Sri Venkateshwara College of Engineering from ISC department. Today we are gonna discuss about data structure. In data structure, we are gonna see about additional list operation. In additional list operation refers to operation that can be performed on list beyond the list operations of insertion, deletion, and retrieval. Some additional list operation include sorting, merging, reversing, and searching. These operations can be implemented using the various algorithms and data structure. List operation has transfers, insert, and delete. These are the various linked list operation that allow us to perform different actions on the linked list. For example, the insertion operation adds a new element to the linked list. Here is the list of basic linked list operation that we will cover in this article. Traverser, insertion, deletion, search, sort. Travels. Access each element to the linked list. Insertion, add a new element to the linked list. Deletion, remove the existing element. Search, find the node to the linked list. Sort the nodes of the linked list. Things to remember about the linked list. Head points to the first node of the linked list. Next point of the last node is null. So if the next current node is null, we have reached the end of the linked list. Here is the example for the structure node. Transfers a linked list. Display the contact of the linked list is very simple. We keep moving the temp node of the next one and display its contacts. When temp is null, we know that we have reached the end of the linked list. So we get out of the while loop. I have given the example with the output of the program. Insert the element to the linked list. First, insert at the beginning. Allocate the memory for the new node. Store the data. Change the data of the new node to the point to the change head to point to recently created node. Second, insert at the end. Allocate the memory for new node. Store data. Transfer to last node. Change next to last node to recently created node. Insert Insert at the middle, allocate the memory and store the data for the new node. Transfer to node just before the required position of the new node. Change the next pointers to the include new node in between. Delete from the linked list. You can delete either from the beginning, end, or from the particular position. There are three types. One is delete from the beginning, delete from the end, delete from the middle. Delete from the beginning. Point head to the second node, delete from the end, transfer to the second last element, change its next pointer to null. Delete from the middle, transfer to the element before the elements to be deleted. Change the next pointer to execute the node from the chain. Space matrices. Space matrices are the matrices that have large number of zero elements compared to the total number of elements. They are commonly used to represent the data that is mostly empty or space. Space matrices can be stored efficiently using the different data structure such as linked list, array, or dictionaries. What is a pair matrices? Pair matrices are whose matrices that have majority of their elements equal to zero. In other words, the pair matrix can be defined as a matrix that has a greater number of zero elements than the non-zero elements. There are two types of spare matrices. One is storage computing time. Storage, we know that a spare matrices contain non-zero elements than zero, so less memory can be used to store the elements. It evaluates only the non-zero elements. Computing time. In the case of searching in spare matrices, we need to transfer only the non-zero elements rather than transferring all the spare matrix elements. It saves the computing time by locally designing data and the data structure, transferring the non-zero elements. Array representation of the spare matrix. Representing a spare matrix by the 2D array element leads to the wastage of lots of memory. This is because 0 is the matrix are of no use. So storing zeros with the non-zero elements is wastage of memory. To avoid such wastage, we can store only non-zero elements. If we can store only non-zero elements, it includes the traversal time and the storage space. Array representation of spare matrix. Representing the spare matrix by the 2D array leads to the wastage of lots of memory. This is because 0 is the matrix and the no use of storing zeros with the non-zero elements is the wastage of memory. To avoid such wastages, we can store only non-zero elements. If we store only non-zero elements, it reduces the traversal time and the storage space. In 2D array representation of spare matrix, there are three fields used here that are rows, columns, values. Row, it is the index of the row where the row non-zero elements is allocated in the matrix. Column, it is the index of the column where the non-zero element is allocated in the matrix. Value, it is the value of the non-zero elements that is allocated at the index, which is rows and columns. Example, let's understand the array representation of spare matrix with the help of example given below. Consider the spare matrix. If the give below a figure, we can observe 5 into 4 spare matrix consisting of 7 non-zero elements and 13 zero elements. The above matrix occupies 5 into 4 is equal to 20 memory spaces. Increases the size of matrix will increase the wastage space. This is the example which is given for the array representation. In the above structure, first column represent the the rows, the second column represent the column, and the third column represent the non-zero values. The first row of the table represent the triplet. The first triplet represent the fourth is stored at zeroth row, and the first column similarly to the second triplet represent the value 5 is stored at the zeroth row, and the third column is in the similar manner. Will all triplet represent the stored location of the non-zero elements in the matrix. The zero of the table depends upon the total number of non-zero elements in the given spare matrix. Above the table occupies 18 to 3 is equals to 24 memory space, which is more than the space occupied by the spare matrix. So that the benefits of using spare matrix, consider the case if the matrix is 18 to 8, then there are 8 non-zero elements in the matrix. Then the space occupied by the spare matrix could be 8 into 8 is equals to 64, where the space occupied by the table represent using the triplet would be 8 into 3 is equals to 24. This is the example which has been given. And this is the output of the program. The output of the first row of the table represent the row allocation of the value. Second row represent the column allocation of the value, and the third represent value itself. And this is the example of and the output. Double Double linked list. A double linked list is a type of linked list where each node consists of reference to the both the text and the previous node. This allows the efficient traversal in the both the direction. Double linked lists are commonly used when the operations like insertion and deletion need to be performed at the both the ends of the list. Double linked list consists of link, next, preview, linked list. Link. Each link of the linked list can be stored a data called an element. Next, each link of the linked list consists of link to the next link called next. Preview. Each link of the linked list contains a list to the previous link called preview. Linked list. A linked list contains the connection link to the first link called first and the last link called last. Basic operations: insertion, insert last, insert after, deletion, delete last, delete, display forward, display backward. Insertion: add an element at the beginning of the list, insert last, add an element at the end of the list, insert after, add an element after an element of the list, deletion, delete an element at the beginning of the list, delete last, delete an element from the end of the list, delete an element from the list using the key, display forward, display the complete list in the forward manner, display backward, display the complete list in the backward manner. Insertion at the beginning. In this operation, we create a new node with a three compartment, one consisting the data, the other containing the address of the previous, and the next node is the last. These are the node in the inserted at the beginning of the list. Algorithm: first start, second create the new node with the three variables preview data, next three store the new data in the data variable. For if the list is empty, make a new node as head. Fifth, otherwise link the address of the existing first node to the next variable of the new node and assign null to the preview variable. 6, point the head to the new node. 7, end. Insertion at the end. In this insertion operation, the new input node is added at the end of the double linked list. If the list is empty, the head will be pointed to the new node. If the list is empty, algorithm: first start, second if the list is empty and the node to the list and the point to the head or to the it. Third, if the list is not empty, find the last node of the list. Fourth, create the link between the last node in the last and the new node. Fifth, new node will point to the null as it the new last node. Sixth, end. Deletion at the beginning. This a deletion operation delete the existing first node in the double linked list. The head is shifted to the next node and the link is removed. The algorithm for this is: first start, check the status of the double linked list. If the list is empty, deletion is not possible. If the list is not empty, the head pointer is shifted to the next node, and fifth is end. Thank you.